Hello everyone. So we will start with three hinged problem, analysis of three hinged problem. So here I will read it out problem for you. A three hinged parabolic arch hinged at the support means hinged at the support at the either side you have support and at the crown. So the third hinge is provided at the crown, has a span of 24 meter. The span of the arch is 24 meter and a central rise of 4 meter. The central rise H here is 4 meter. It carries a concentrated load of 50 kilonewton at 18 meter from left support. So from support A we have 50 kilonewton load at a distance 18 meter from support A. So this is 24, and from support B it will have 6 meter. 50 kilonewton load will have 6 meter from support B and a UDL of 30 kilonewton over left half portion. So the entire left half portion is having UDL of intensity 30 kilonewton per meter. So what we have to determine here? Determine the moment, thrust means the normal thrust, and radial shear at a section 6 meter from the left support. So at a distance 6 meter means I have defined here point D, which is 6 meter from A. At point D we have to determine moment, we have to determine normal thrust and radial shear. Okay, so first we have to start with the calculation of support reaction. So we have support A, support B. At support A you have two reactions, VA and H, and at support B you have two reaction, VB and H. So H will remain same whether you have symmetrical arches or unsymmetrical arches, the H will remain same. So how to find this VA? So in order to find this VA we have to take moment about B, which is equal to 0. Now you make an equation here, taking moment about B from A to B, considering all the forces from A to B. VA into 24, VA perpendicular distance from B is 24, and this is creating clockwise moment. Then you have this UDL. The total load of the UDL is concentrated at the center. Okay, and perpendicular distance from B is 18 meter, because this is 6 meter and this is 12 meter, total comes to 18 meter. So minus, and this will create anti-clockwise moment with respect to point B. So 30 into 12, which is total load, into perpendicular distance. Okay, so then you have this point load, and the perpendicular distance from B is 6 meter, and this will also create anti-clockwise moment. So minus 50 into 6. So VA you will be getting 282.50 kilonewton. Now when you got VA, you can easily find VB. You have to take summation of f of y equal to 0, VA plus VB, because both are going upward, and this UDL is going downward, minus 30 into 12 total load of the UDL minus 50. So VB you will be getting 127.50. We also have horizontal reaction here. How to find this horizontal reactions? We have to take this point C, joint C, wherein you have internal hinge. So at internal hinge the moment is 0, and you can make use of that equation. Now you can choose any span, you can choose span AC or span BC in order to find this horizontal reaction H. So here I have taken span BC. When you take span BC, you have to travel from B to C, means from right to left. Here clockwise moment will be negative, anti-clockwise moment will be positive. Okay, so now see here, what will be equation B to C? H. This is the line of action of H, and perpendicular distance from C is 4 meter, and this H is creating clockwise moment, so we have to take negative minus H into 4. Then you have VB, the value of VB is 127.5 kilonewton. VB into perpendicular distance from C is 12 meter. Okay, and this VB will create anti-clockwise moment with respect to point C. So that's why VB will be positive here, and this 50 kilonewton, which is having 6 meter perpendicular distance from C, will create clockwise moment. So we are following a direction, by that direction clockwise moment is negative. So H you will be getting 307.50 kilonewton. Now after reaction, you can read in the problem, we have some purpose to find. In the problem we have to find moment, thrust and radial shear at a section 6 meter from left support. So 6 meter I have defined a point D, which is 6 meter from A. So I have drawn here the free body diagram of span AD or the section AD. So what we have to do here, we have moment at 6 meter from left support, normal thrust, radial shear at 6 meter from at the same point. Now see here, for that I have taken a free body diagram of A to D. So here you have to show the reaction VA and H, which is at A, and this X is 6 meter. Okay, now we have to calculate moment at this point. So this vertical distance I will take YD is vertical distance, and from horizontal distance of D is x meter, and vertical distance from here to here is YD. Okay, now see here, we know this horizontal ordinates, X we know, but we have to calculate this vertical ordinates. So we are dealing with parabolic arches. We have the relation between y and x. Y is vertical ordinate, any distance, any vertical distance. What is the vertical distance at x equal to 1 meter, x equal to 2 meter, x equal to 3 meter. So we have the relation for parabolic curve, parabolic arches. So the relation between y and x is y equal to 4hx in bracket L minus x bracket complete divided by L square. H is the rise means the central height of the crown, or you can say height of the crown from the support level. So here in this problem H is 4 meter. Okay, and L is the span of the arch, which is 24 meter, and X we know X. So at 6 meter we have to calculate this vertical distance of point D. So substitute the value, 4 into 4, H is 4, X is 6 meter, L is 24, 6. So you will be getting this 3 meter. YD is equal to 3 meter. And now see how to find moment at this point. We are following a direction of from A to D, means left to right, clockwise will be positive, anti-clockwise will be negative. Okay, so VA into 6 meter creating clockwise moment. VA, the value of VA we know, into 6 meter. Then you have this horizontal reactions. We know the value of horizontal reactions, 307.50 into this vertical distance, because this is the line of action of horizontal reactions, and we are calculating moment about point D. So we have to know the perpendicular distance the perpendicular distance from D to this line of action, which is 3 meter, and then you have this UDL. Total load of UDL is 30 into 6, because this is 6 meter. This is the line of action of total concentrated load, and which is 3 meter from D. So this will create anti-clockwise moment. So you have this anti-clockwise moment. So moment at D is 232.5 kilonewton meter. Our next purpose in the problem is to find normal thrust, radial shear at 6 meter from left support from A. So at point D we have calculated moment at point D. We have to calculate normal thrust and radial shear. Before that, we will understand what is normal thrust and how to derive the formula for normal thrust. First, we will try to understand what is normal thrust and how the formula is derived. Now see here, normal thrust is normal to the plane, and this radial shear is along the radial direction. So that's the name radial shear. Now how to derive the formula? I will just draw a free body diagram like this. At this point, I may have vertical shear, I may also have horizontal reaction at this particular point. Okay, so normal thrust will be like this, which is inclined theta with respect to horizontal, and this vertical radial shear, this will be like this. This is inclined, this theta and this theta are equal. Okay, so first we will understand how to derive the formula for normal thrust, and then we will derive the formula for radial shear. So this is horizontal reaction theta, vertical shear is like this. Okay, so this is normal thrust axis. Axis means the line of action. Okay, so I am defining it as normal thrust axis. If I just elongate draw like this H, it will be okay. H is having theta from normal thrust axis, so this is also normal thrust axis theta. And the direction of normal thrust is in this way, we are assuming in this way. This is the direction of normal thrust. And V is having this is theta, and this will be 90 minus theta. Okay, so what we have to do here, this horizontal reaction and this vertical shear, we have to resolve this in normal thrust axis. Okay, so this horizontal reaction, if you want to resolve horizontal reaction along this axis, so it will be normal thrust equal to H cos theta. H is having theta with respect to normal thrust axis, so the resolution of H in this direction will be H cos theta, and it is along this direction, it's not against. This resolution of this H is along direction of N, so that's why it is positive. Now see here, vertical shear, V is having angle 90 minus theta with respect to normal thrust axis. So along this axis it will have cos component. Resolution of vertical shear along this axis will have cos component of angle 90 minus theta, and it will be along this direction, not against this direction, along this direction. So that is why plus V cos 90 minus theta. So I can rearrange this formula normal thrust equal to H cos theta plus V sin theta. So this is the formula of normal thrust and we can use it. Now we need to understand how to derive formula for radial shear. Now this is the direction of radial shear, so I can call it as this axis, radial shear axis, radial shear axis. Now see here, vertical shear V is having theta angle with respect to radial shear axis. Okay, so what we have to do here, this H and this V we have to resolve in this direction. We have to resolve in radial shear axis direction. Now when you resolve this will have cos component. Okay, this V, vertical shear, will have cos component. The resolution of V will be cos component along this direction, and it is against Q, not with the direction of the Q, against Q, opposite to the Q. So that's why we have to take minus V cos theta. Okay, now see here, H is having this is theta, this will be 90 minus theta. Okay, so H is inclined 90 minus theta with respect to radial shear axis. So the resolution of H will be H cos 90 minus theta along radial shear force, not against radial shear force, with radial shear force. So it will have positive value, H cos 90 minus theta. So when you rearrange, it will be like this, Q equal to H sin theta minus V cos theta. So we have derived the formula for normal thrust and radial shear. This is the normal thrust formula and this is radial shear formula. Now see here, we need to understand something about formula. The sign of H, here it is positive, the sign of H will not change. The reason is that in case of arches, H, it will always be towards the joint, not away from the joint. It will always be towards the joint, and we have derived our formula by taking H towards the joint. So in case of arches, H, it will always be towards the joint and the sign of H will not change. We don't have to change the sign of H, but the sign of V will change. Okay, so we have derived the formula of normal thrust by taking V downward. We have derived the formula of radial shear by taking V downward. Sometimes it is possible that you may get V upward, vertical shear upward. If you are getting V downward at particular section, then don't change the sign of V. If you are getting downward vertical shear, don't change the sign of V. Sometimes it is possible that you may get vertical shear at particular section upward. So in that case, you have to take here minus V sin theta. Here you have to take plus V cos theta. Okay, so that thing you must remember in order to solve for normal thrust and radial shear. Coming back to problem, we have to calculate normal thrust, radial shear at a distance 6 meter from A. So for that, you have to draw free body diagram. Okay, so free body diagram in this way you have to draw. Okay, now free body diagram. So at this point you have to calculate normal thrust and radial shear. What you have to do at this point, you have to find H, which will remain constant, so the value of H will not change. But what is vertical shear at point D? We have to find. So assume that VD is downward. If you are getting positive, then your assumption is right. If you are getting negative, then change the direction of VD. So when you are assuming VD downward, you use this formula summation of f of I equal to 0 and apply here. VA is going upward and 30 into 6 is going downward. So VD you will be getting 102.5 kilonewton. So you got positive. Whatever direction you have assumed is right, and see here it is downward. Here it is downward. Now we have calculated H at point D. We know VD at point D. We can use this formula, normal thrust formula. H we know, V we know. So now we need to understand how to find this theta. How to find this theta? See, angle angle is changing from point to point. At A angle is different, at D angle is different. You just have to draw tangent. Okay. Now how to find this theta? Here, see, tan theta equal to dy by dx. Tan theta equal to dy by dx. Theta equal to tan inverse of dy by dx. So we have to find this dy by dx. We know y formula for parabolic arches. Vertical ordinate y, 4hx L minus x divided by L square. Derivate this formula with respect to x, you will be getting this. Okay, so here theta equal to tan inverse of dy by dx, you got dy by dx. So theta equal to tan inverse of dy by dx. H you know, 4 into 4, L you know, so everything you know. Theta you will be getting 18.435. Now you go for the calculation of normal thrust, equal to H is 307.50 cos 18.435 plus VD equal to 102.5 into sine 18.435. So N you will be getting 1 minute. So after solving you are getting normal thrust equal to 324.13 kilonewton. In the same way you have to find radial shear. This is the formula of radial shear, H sin theta minus V cos theta. I told you the sign of H will not change, but the sign of V it will change. But in our case VD is downward, so we don't have to change the sign of V because VD is downward. So after solving this, you are getting radial shear equal to Q 2.89 into 10 raised to minus 4. So we have completed the problem. Thank you.